So what are we talking about, Dr. Hunter?
I wanted to just go over some phase diagrams because um, it just, I don't know. Every time we look at a diagram in this course, I think, man, there's a lot of information in there. And I think if I'm thinking there's a lot of information, then maybe students don't realize how much information there is because they're actually they're a little overwhelmed by it. So let's go look at a couple of pictures here. So looking at this phase diagram, and I mean, as we've talked about at other times, when you are confronted with a document like this, I think it's probably a good idea to look at the axes. And so we figure out that if we look at this one, we can see that its temperature is changing along the bottom. And to be fair, the temperature scale is really weirdly compressed because here's 0.01, here's 100, and here's 374, right? So this is by no means is this a linear scale. I think so this line that curves so nice and smoothly here or here, I'm sure that if this was a linear scale, it would look super, super flat, and it would just be basically a flat line going across the page like this. But at the bottom, it's showing the temperature. And so these are low temperatures on the left and high temperatures on the right. And then here is pressure, and it's measured in atmospheres, and it's the atmospheric pressure. And so this is a graph that just says what happens to the this substance, which in this case is water, at these various temperatures and the temperatures and pressures. And the hard part for me when I look at this diagram is I forget that in my life, I am just almost all of my life is hanging around this line, right? I mean, this is atmosphere pressure 1. So, and the variation on a day-to-day basis of the atmospheric pressure is minuscule. I mean, sure, if we have a really great day, you have a slightly high pressure, and if you have a really crappy weather day, then you get a slightly lower pressure, but it's basically always at this line. So somewhere along this line is where you and I exist. And frankly, the outside temperature hopefully never gets to be 100 and hopefully never gets to be 0.001. I mean, I guess sometimes it gets to that, but where you and I live, water is just around this little circle that I'm drawing with the arrow right now. This is where we exist. So these other high pressures or low pressures down here, or low temperatures and high temperatures, we never see them, right? I mean, only in specialized lab situations. So it's hard to understand what's going on with this diagram because it doesn't really relate to our lives very much. It's very, 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 very specialized. And so if I look at it the way that you and I are typically look at it, which is to say, okay, if I'm gonna boil some water on my stove, well, I'm doing it at about 1 atmosphere and I'm doing it at 100 degrees Celsius. So this point here is us boiling water on a stove or in a kettle or something like that, or in a microwave. And another place that you and I exist is down here when we cross this boundary, when we turn liquid water into solid water in the freezer compartment of our refrigerators or our freezers, or outside on a cold winter day when liquid water turns into solid water. So we see this point as being the freezing melting point of water, and we see this point here as being the normal boiling point. And I think it doesn't mean normal Illinois. I think it just means normal as in the way that most humans on the planet live. But maybe we got a personalized textbook today. I don't know. So we see these 2 points. And so this is the point where we have it going from just slightly liquid, close to 0 degrees Celsius, to freezing across here. And so this line here, line B, is a freezing point line. What happens to the freezing point of water depending on what pressure the water is experiencing. And this is the boiling point line, or boiling point, normal boiling point. This line from this T up to C is what happens to the boiling point of water when we change the pressure on the surface of that water. How am I doing so far, Kevin?
Yeah, I think that all makes sense, that vertical is more pressure and we're not really used to it. And especially with the axes again, because just like you mentioned with temperature, how that scale is not linear whatsoever, the pressure scaling on the vertical side is not to scale whatsoever. In fact, it might be more crazy, at least from 1 to 0.006.
Yeah, and that's a good point, because you and I, we've seen these temperatures, right, all the way across where I'm moving the arrow right now. We experience those temperatures. We never experience these pressures up here or down here, right? I mean, so that's a good point. So if there's crazy talk on this graph, it's probably the pressure crazy talk. It's not, the temperature is in the realm of possibility for it, but the pressure is not. I mean, if you dive down in a swimming pool, if you go down 14 feet, well, then you get basically double atmospheric pressure, so from 1 to 2. And anybody that's been in scuba diving or down below the surface in the ocean, if you go down to like 32 feet, much more than that, you are in, it's serious pressure. And that's just barely moving off of this axis here, right? So this 218, we're talking about being on Jupiter or something. I don't know how much atmospheric pressure is on Jupiter, but 218 is some, you and I'd be squished like a bug. I assume we would be.
Yeah, that sounds
okay.
way too much.
So why did they bother putting this diagram in here?
Why did they?
Well, I think it has, the thing that's interesting about this is that you would think that with a substance like that, if we increase the pressure, okay, so if you increase, let's look at the boiling point. So if we increase the pressure above water, in order to get it to boil, you have to increase the temperature some more. Okay, so because boiling is liquid molecules turning into gaseous molecules. So they are separating from each other, going from left to right on this diagram. The molecules have to get further apart from each other. So you can imagine that if I increase the temperature by going up, now I've got more atmospheric pressure pushing down on the surface of that water. And so it's harder for the water molecules to escape. And so since it's harder for the water molecules to escape, we got to get to moving a little bit more in order to get the temperature, and get the temperature high enough to allow them to escape and form a gas. So the fact that from this boiling point right here that we normally experience, going up, if we increase the pressure, we also have to increase the temperature to get it to boil. So the upward rightward slope on this boiling point graph makes perfect sense. Well, I don't know if it makes perfect sense, but it seems reasonable to me that we should have a positive slope as the pressure increases, because we got to increase the temperature, make the molecules move even faster to get them to escape from the liquid.
Yeah, that makes sense.
Okay, so then what about over here? Here we've got a slightly negative slope, right? That as we decrease the atmospheric pressure, as we increase the atmospheric pressure, what's this temperature? This is the freezing temperature of water, right? And so as we increase the atmospheric pressure, apparently it changes the ability of the liquid and to turn into the solid, right? It becomes apparently at a slightly lower temperature. And the reason that is that liquid water molecules are just moving smoothly and slowly, well, however fast they're moving. They're moving over each other in a relatively unregulated pattern. But in order to form a solid, for the same reason that we see snowflakes with their hexagonal pattern, for the same reason that ice cubes increase their volume in an ice cube tray when you make them, for the same reason that pipes freeze and crack the pipes when they expand. When water goes from being a liquid to a solid, it increases its volume a little bit. And so going from a liquid to a solid, if we increase the atmospheric pressure, we have to actually reduce the temperature a little bit more in order for it to be able to expand the way that water wants to expand, right? And so we're increasing the pressure on top. It's harder for the solid water to form because it wants to expand. And so we have to slow those molecules down just a little bit more. We have to decrease their temperature just a little bit more for them to be able to form into that expanded solid structure. And so that's why this liquid to solid graph along point B, along line B, is slightly negatively sloped.
Yeah, that really makes sense. I didn't really consider water expanding when it freezes, because I think all other substances, they kind of compress even more from liquid to solid. So you would normally think that when you increase pressure in this scenario, that the freezing point would go the other way. The slope would go the other way.
Yeah. So if we find, maybe we can find one, but if we find a graph for like other substances, this line B, instead of sloping up to the left, for other substances will slope slightly up to the right. Okay, so here's carbon dioxide. Okay, so it doesn't look exactly the same, but here's temperature along the bottom. Here's pressure along the vertical axis. Here's this nice liquid to gas boiling temperature for carbon dioxide. Looks a lot like the water graph. But if you look at from this point going across the solid liquid boundary, you'll see this one. Does it look like it slopes to the right to you? It does a little bit to me, but it may also look like it's just completely vertical to you.
Yeah, very slightly to the right. I think you can even see the pixels.
Yeah, exactly. And maybe I can zoom in a little bit. Is that getting better if I zoom in like that? So this substance, carbon dioxide, this solid liquid line is slightly to the right, slightly a positive direction. I wonder if we can find another one. Oh, it was on Chegg. Don't use Chegg. Well, use Chegg when you're allowed to use Chegg. Don't use it other times. This is the phase diagram for ammonia, right? It says not to scale. I appreciate them saying that because it's definitely not to scale. But here is temperature along the bottom, pressure of atmospheres along the right, liquid gas line, solid liquid line, and goes up to the right. Water is pretty unique in terms of its expansion when it freezes. Almost everything else contracts when it freezes. What else should we say about this, Kevin?
I'm a little curious about when you decrease the pressure by an extreme amount, you can see there's from a line A, solid to gas.
Yeah. So I'm drawing a blank on why that occurs, but it's clear that it goes straight from being a solid to a gas without going through the liquid phase, right? Because typically where you and I live, hey, we've got some ice. I can take my ice. I'm going to melt it. It's going to be liquid for a while, and then it's going to turn into a gas. Down here, then there's this interesting place where a triple point where you can have all three phases simultaneously. And I do remember as an undergraduate, and I think maybe that there's in some of our third year courses, they do an experiment where they force something to exist at its triple point. And so you can see the solid, the liquid, and the gas simultaneously. But down here, it is definitely a transition that takes place directly from the solid to the gaseous state. Trying to think, why is that? Why does it not have to go through a liquid? Are you remembering why that can happen, Kevin? Because I'm drawing a blank on it myself as well.
Well, so what I'm just kind of thinking about is that there's just so little pressure that it's kind of hard for the molecules of water to kind of exist in this fluid state.
Right.
They rather have to stay compact, solidified, or they just fall apart. And like we were talking about, we live in this 1.0 atmosphere pressure that there is this middle phase where they kind of just melt or fluid out. But when there's so little pressure, it just fluiding out becomes more gassing out. There's nothing containing them, making them kind of stay in their container like a liquid does.
Right, and so over here on the solid side of this line, the intramolecular forces are strong, are still strong enough to hold that thing together as a solid. But there's basically but once we cross that point, now a molecule escapes and it's gone. it's gone like a gas, right? Yeah, and that that the intramolecular forces are basically non-existent. So it goes from having some to having basically no intramolecular forces.
Like you said, there's just so much information condensed on here. So usually how I approach phase diagrams is just kind of remembering, and most of them are labeled where the solid region is, where the liquid region is, where the gaseous phase is. If it isn't, then it's almost always solid on the left, gas on the right, liquid in the middle, just like the 1.0 atmosphere life that we all live in.
Yeah.
But when we change pressures, that's when you have to be careful about the vertical axes and the horizontal axes, and reading the diagram, reading the graph very carefully.
Yeah, I mean, it is a classic question that I don't know whether whether Cengage asked this question, but a very classic question is to have a phase diagram and not have solid, liquid, and gases labeled, and then to ask you what happens as some of these transitions, and maybe they'll put a little spot in one of these locations and say what phase is the substance of that particular location. And but if it's low temperatures, then it's almost certainly going to be more solid on the left with low temperatures, right? Just like we experience, just like we know already. And if it's high temperatures, then it's going to most likely be boiling in gases on the right-hand side, almost always. And I don't know if anybody ever tries to mess with people's heads by flipping the axes and that sort of thing, because where they're trying to just make the questions a little harder or whatever. Maybe I'll do that one day. I don't know. I have no intention of doing it. But if you think about what your experience is, what our experience is, where do we live? We live at 1 atmosphere. We live in this region, and then start to just dissect the graph from there. That can make it manageable.
Yep.
Is there anything else we should say about this, Kevin?
No, I think that's it for phase diagrams. It's just a lot of information, so be careful.
Yeah. Awesome. All right. Thank you, Kevin, very much.
Thank you, Dr. Hunter. Talk to you next time.